Welcome everyone to the fourth Direct Write Lithography workshop and the RIE Etch webinar series, and welcome to webinar number 3 out of 7. Before we start with the webinar, I'd like to acknowledge the traditional owners of the land we are gathered here today, which in my case is the people of the Kulin Nation, and I'd like to pay my respects to their elders past and present. Furthermore, I'd like to acknowledge the Australian National Fabrication Facility and its CEO, Jane Fitzpatrick, for their ongoing support. I also like to acknowledge our panelists and facilitators who helped to arrange the webinar series. And especially for today's webinar, a big shout out to Jörg Hübner, who is also on the call, for getting us in touch with Henri, who generously agreed to run those 2 webinars for us. And of course, the whole workshop organizing committee for putting all the hard work into it. And that brings me to webinar number 3. I already mentioned it in the email I sent, I believe yesterday or the day before yesterday. We were quite lucky to secure a 7th webinar, which will be held for the Australian attendees on the 30th of April. This is a sponsored webinar, and it's from KLA. You can see it on the updated template and the program I shared as well. So today we welcome back Henri Jansen from DTU to present us the physics and chemistry of plasma etching part 2. And before I hand over to you, Henri, quick introduction again. Sorry, here we go. Henri was born in the Netherlands in a town called Marienham at the eastern countryside, inhabited with more cows than people. As a kid, he joined the dangerous social Dutch soccer events, and after being hospitalized 2 times, he decided to try his luck with single-person sports events, like long-distance running and cycling. After doing military service in the Dutch Royal Navy between 79 and 85, and having seen many astonishing scenarios abroad, he started his academic career. From 85 till 91, he did his master's in science study at the University of Twente, with special topics in quantum physics and material science. In 1996, he got his doctorate degree in, and now for something completely different, under guidance of Professor Dr. Jan Vloetman, with the thesis Plasma Etching in Microtechnology. From this topic, he became locally well known as the Black Silicon Man. Then he entered for 2 years the dark side of his academic career to develop plasma engineering in the industrial environment. In 89, though, he rejoined the academic playground to give assistance in education and microengineering at the University of Twente, and was promoted to become associate professor in 2003. Then in 2016, he took the final rung of his academic ladder to become full professor at DTU Nanolab, where he continues to play as full-time plasma engineer until today. He has been supervisor of numerous students over the past years, resulting in 120 publications that have been cited over 6,500 times, and causing an age index of 42 in Scopus. And we are very lucky to have him back again. Henri, the stage is yours. Let me stop sharing. And yeah, please go ahead with webinar number 3.
Good. Why do I see no 2? Share. Are we there? Yes. Oh, I don't hear you anymore. Oh, you're unshot. But I saw you saying yes.
Perfect. Yeah.
Good day. Good day all. So I say good day because I have no idea exactly where you're all coming from. This will be the second session. Previously, you might remember that we did a little bit more about gas fundamentals and plasma fundamentals, which is like the core of the plasma itself. But of course, that's not the final piece of puzzle we need. We need another piece, and that's how does this plasma now interact with our wafers, because we want to etch it. That means I'm now going to say something more about plasma etch fundamentals. So that's the interfacing between the plasma and the wafers to be processed. And then after a short 5 minutes break, I will show what kind of things, if you really understand these 3 previous pieces of puzzle, how can you put it into a nice, let's say, structuring or sculpturing of structures. Then For the plasma fundamentals, so the first part of this day, the first hour, let's say, I will talk a little bit more about what is exactly plasma etching. It's very short, right? Then about etch mechanisms, then etch chemistry, etch thermodynamics, and then we'll talk a little bit more about etch rate, which is a function of all, let's say, reactor parameters. Then, let's say, what I call the black silicon method, and then based on that, we can see a little bit profile loading, RDA lag, and how this etch directionality is, let's say, how does it influenced. That last piece I will probably skip. That has to do with time. But okay, let's start with the plasma itself. A little bit of overview how it roughly works. And typically, the process starts with evacuating a reactor and letting in an etch gas and stabilize. Let me try to see, can I minimize, because I see a lot of extra things on my screen which I don't like. Yeah, so there are many things in front of my view, therefore I had to skip that. Good. Then we use an ICP source to crack the relatively stable molecules forming chemically reactive and ionic species. And we add an CCP source that creates an electrical field to direct the positive ions towards the wafer. And choose the symmetry such that these species react with the solid to be etched to form volatile products. As an example, you see here how SF6 is cracked into SF6 plus ions plus an extra electron, which is doing the plasma. So this is for the valence. Then we have here the SF6, which also can be cracked into SF5 plus F. That's the radical. That's the one who normally is going to be etching the silicon. And here you see how it etches with the silicon. The silicon is very reactive with the fluorine radicals and causing silicon tetrafluoride, which makes me that I have to take the pointer. What was it again? Here, laser. Yeah, good. There we are. Now, 4 types of reactions can take place during etching, depending on the etch gas used to etch the material. It is chemical isotropic etching, which is causing undercut, physical sputtering, causing tapering, and 2 ion-enhanced types, so the ion inhibitor and ion-induced reactive ion etching. The isotropic etching is more like wet etching. And a typical example is how the silicon reacts with the fluorine exothermically, creating the volatile, very volatile silicon tetrafluoride. And more an example of sputter etching is like ion milling, where, for instance, the noble ion argon is with high velocity directed towards, let's say, a silicon surface, and it just kicks out a silicon atom, which is, let's say, airborne. It's not, I would not call it volatile, but just airborne, and then redeposit somewhere else, but you knock it out. Pure physical, this one. And then the 2 most important ones, that is ion inhibitor and ion induced. Ion inhibitor is, in a way, still depending on the isotropic etching, in the sense that the material you want to etch is still very volatile. To prevent it from undercutting like isotropic etching, what we do, we introduce an extra gas which is inhibiting it. So it could be oxygen or fluorocarbon in some time cases. Here I take the example of silicon oxide, the oxygen, because it will create silicon oxide, which is non-volatile. But now we add also the ions, which are coming out of our plasma, and we have, let's say, the DC bias, which is controlling it, and the plasma potential, and they are directional. So these ions will then knock out again the oxygen, which is just coming to the surface. It will knock it out again. But it can do that only at the places at the bottom. And the side walls are not seeing the ions, and therefore they are protected by the silicon oxide. At the bottom then, though, they were removed. And then the fluor radicals, who are just waiting here all the time in huge quantities, because we remember maybe from the plasma fundamentals that the radicals are normally like 100 times more available, let's say, than the ions. So the radicals are just waiting to attack again the silicon, which has just been freed at the bottom by the impact. And you get again silicon tetrafluoride. Due to this process, it's quite fast. It can be very fast because this one is still the reaction controller. Then we have the second type, which is, I can first also show it. It's kind of called ion induced, with the silicon oxide. But now we are not etching silicon, but we are going to add silicon oxide. And in this case, still the ion will remove the oxygen and knocking it out. And here, again, let's say the silicon, which is then coming available, will be removed by the fluorine into silicon tetrafluoride. But in this case, all the time, we really need the ion to crack every single oxygen molecule from the silicon oxide lattice. That means that the etch rate here is much more solely controlled by the ion density. Whereas in this case, for the ion inhibitor, because we still have this huge fluor radicals, as soon as the bottom is freed, it can really go that every ion can etch like 100 times more silicon. So normally this ion inhibitor etching is much more faster and directional than the ion induced. The disadvantage though is that this one you have to control very well because this is really a balance. If you do a little bit too much, you will get undercut. We will see that later. Then finally, another type of ion induced, which is related to this one, is if you would not use fluor radicals, but chlorine radicals and ions. What here, when you use a chlorine plasma, before when you have fluor, the fluor radicals are so small, they can penetrate the silicon lattice. So they can even etch, let's say, the silicon lattice from the backbones. Therefore, it is very, let's say, spontaneous and easy to etch. However, for silicon, the chlorine atoms, when they have, let's say, attached to the top side of the silicon lattice, which are freely available, the backbone of your silicon is very difficult to catch by chlorine because they cannot enter, let's say, let's call it the passivation of silicon chloride. And only by impact of ions, it can dislodge the bottom side and then it starts to etch. So it's also this one, it has to wait for the ion before the backbone of the silicon tetrachloride, silicon trichloride in this case, will be becoming volatile. This is volatile, but you need the ion now. Also, this one is relatively slow. So reactive ion etching is the main actor in modern semiconductor fabrication facilities. And this is because we just saw it faithfully transfers the resist pattern into the underlying layer. Many gases now are used depending on the needs, but mostly containing the halogens, like BCl3, Cl2, F2, etc. As we talked about, so these gases just we talked before, the chlor and bromine based plasmas, they are creating, yes, the radicals we are needing, but it is a self-blocking reaction. So it really needs to catch the backbone. So really it needs ions to get directionality. Therefore I would call it ion induced, low etch rate, but straight. The other types are all the fluor, what you see over here, from let's say fluorine up to SF6. They are creating the fluorine radicals, making the very volatile silicon tetrafluoride product. And this is now normally a spontaneous reaction. So it needs the inhibitor like oxygen or C4F8 or CF2 species. And then the ions still have to knock it out to get the directionality. Ion inhibitor reactive ion etching. High etch rate, straight. More difficult to control. Now, why are we using halogens? Well, in a way, look at the periodic system, and these are the let's say these are the elements who are very close to the noble materials, and they are, let's say, missing an electron in the outer skin, outer skill. So they really have a strong affinity for electrons, and therefore they are very strong oxidizers and becoming very reactive with all the others. So they really want to do, let's say, they will create try to create compounds with the other metals in the periodic system. Okay, now we would like to sculpture. So we are like to etch now inside our reactor. And we would like to create a directional etch with a certain material. Then the first thing we have to do is we have to look at the correct reactive ion etch mechanism. That means, first of all, check the material composition. So for the elements from the periodic table we just saw. And based on that, we have to choose a plasma chemistry. It can be fluor, bromine, or maybe even carbon monoxide. And then we find and choose a mass material that can withstand this plasma too, because we need to sculpture it and something has to withstand it on top to make our device. Then our topography. And after that, the final one is we have to make sure, and that's the most important one, and I'm going to discuss that now in a few slides, is make sure that all the reaction products are volatile. And for that, we have to check the boiling temperature. How are we doing that? Let's say we take an element you would like to need. So we have looked in our material we have to etch away, and we know what is inside. And now we're going to check in the databases, like it can be Wikipedia, Web Elements, periodic table, or Copilot. We have to look for a compound, a halogenated compound with the lowest boiling temperature point or temperature. For instance, let's take molybdenum, which is over here. I check with what kind of compounds are there with molybdenum. For instance, molybdenum hexafluoride, I find in the databases that it boils at 34 degrees. For molybdenum pentafluoride, I see that it sublimates at 50 degrees. And for instance, for molybdenum hexachloride, it says it will decompose. Decompose means it goes down to a lower halogenated species or compound like MoCl2, molybdenum pentafluoride. That one boils, so that means that we cannot use it at all because we have to find the lowest boiling point. And then we go for molybdenum pentafluoride, and it says 268. With these two numbers, I see this is the lowest and this is the lowest for the chlorine. We put it into the table. So 34 and 268 for the chlorine. So what you see now here is all the elements. We wrote it down here, and I write down all the time for fluor, the lowest, for chlorine chemistry, what is the lowest, and here for the bromine, etc., etc. I make now blue all the compounds which has a boiling point below 300 degrees. I do this because that's for me an indication that they might be etchable, but I'm not sure. So, and therefore I have to check a second part we need of this graph is the vapor pressure. Let's take an also maybe not everyone is totally aware of the vapor pressure and what it means. I will take first an example everyone knows, and that is water. Here you see the phase diagram of water, where you see where is it solid, liquid, and vapor. The most important points you probably all know, well, you should know, is that here, this line, this red line, is 1 atmosphere. So that is room pressure along this line. And we all know that it boils. Here is the line where it starts to boil. It goes from here, from liquid into the vapor. So this is the boiling point. And if you would go further down, here we know that it is freezing at 0 degrees. But in fact, when we are busy with water trying to vaporize it, then we know that if you go to a lower pressure, that the temperature of boiling is also going down. You can see that, for instance, if you go uphill or up mountain for the Mount Everest, every 300 meters raise in altitude will lower the boiling temperature by almost, let's say, 1 degree Celsius on average. So on the top of Mount Everest, the boiling temperature is only 70 degrees. So that's here somewhere. If we would follow this, it is a kind of a logarithmic curve. So materials vaporize, and that's true for every material or compound. So materials vaporize logarithmically easier at lower pressure. But now exactly what is that relation? Yeah, logarithmically. Yeah, what? What is the number? And there are two approaches. Experimental, using the Antoine equation, or theoretical Clausius-Clapeyron. That's the two I'm going to treat now. That's the first one, the Antoine equation. So because he already know that it is a logarithmic behavior, he just wrote down an empirical correlation, which is the 10th logarithm of the pressure, or the vapor pressure, is a constant A minus a constant B divided by another constant C plus the temperature we are looking at. So the P is the vapor pressure, T is for temperature, and ABC are the substance-specific fitting parameters determined experimentally. And they are tabulated for many substances, and you can find them here maybe in JAWS or in SPITE. So there are books full of Antoine coefficients. Not all of them are there, and we don't talk about that directly. But for instance, we have water between 1 and 100 degrees, and the set of Antoine constants we can use, and they are in this case then given in torr and degrees Celsius. So these numbers are specifically for the pressure we are looking at. Of course, you can always convert them in each other, but if you see this one, you have to know, because you say here a logarithm of a pressure, which is normally forbidden. So you have to divide it by another pressure, which is your constant pressure. And you can do that in torr. You can say this is in torr, but it's the numerical value. And here you would then write down for the temperature the numerical value, but in degrees Celsius. So you don't write 100 degrees Celsius, but you write 100. You put in the numbers, and then you find, for instance, at 20 degrees, that our vapor pressure is 2000, roughly 2000 Pascal. This is expected because this it matches nicely the well-known value of the real value of 2339 Pascal, which is not so strange because it has been fitted for that. So it is really a brute method, but a lot of numbers are well known, and therefore it can be quite accurate if you want to know. But this correlation is, of course, only valid over the range for which the constants have been fitted. If you go out of that scale, so if it's not fitted for, so this one has been fitted between 1 and 100. If you would use this one for 200 degrees, you would be really going off the line. Or if you go below 1 degree, it's going to be bad. That's the first thing to say. The second one is that, well, sometimes we have such a weird plasma product, we don't even know the Antoine parameters, because, yeah, who did study something like silicon tetafluoride? Well, this one is known, but not all, let's say, that type of chemicals are known. Then we have to go back to, or we have to go to the theory. And we start with the general Clapeyron equation, which is an exact differential equation derived from thermodynamics. It says that the dp dt is the change in entropy divided by the change in volume, or the change in enthalpy, or the change in entropy divided by the change in volume, and which is the same as the change in enthalpy divided by the temperature times the change in volume. Now, using the ideal gas law, which is, we remember from the first session, P times V is RT, the Clausius-Clapeyron can be derived for the liquid-gas transition of vaporization, because that means the PdT is, we fill in dV and we use this gas law, and we find that it is the enthalpy of vaporization divided by the gas constant times pressure over T squared. Now we can rearrange these parameters. If we take the P over here and we take the T over there, which is the same here, and now we know that dP is in fact the LNP. It's just mathematics now. So this is our famous Clausius-Clapeyron equation for the transition for liquid to gas. So it calculates the change in vapor pressure of a liquid at a certain change in temperature. But it only applies to vaporization of liquids where the vapor follows the ideal gas law, so Vp. So this one was needed to get this one. So that's the first thing. Furthermore, it assumes that the liquid volume is neglected as being much smaller than the vapor volume. So when we make a transition, let's say most of the volume is going to be occupied by the gas. Well, a little star. Well, this assumption, it sounds like a harsh one, but it is in a way almost always true, because we already knew also from the previous lecture that the molar volume of a gas at RTP is about 100 times more than its liquid form. So at room pressure and temperature. But even at 30 Kelvin, so very close and very cold, it's still 100 times more volume for the gas than for the liquid. So in a way, it sounds harsh, but this is normally quite true for at least all the things we are going to do in plasma etching, because we are never going to etch at 30 Kelvin or below. So we are typically etching at room temperature. So therefore, and it's even worse, we will see later, because we are not going to be, or even better, I should say, because we are not etching at 1 bar, where this is 1,000, but even at very low pressures, that like 1 millitorr or so, or 10 millitorr. And then this number is huge. So it means that this, in general, is, I would say, always true for us. Then the last, this differential equation, we can integrate from the known pressure and known temperature, where we know these two numbers, and we can then find two numbers we don't need, so that we say we would like to know the vapor pressure at a higher temperature or a lower temperature. If we integrate, and we just get the natural logarithm of P over the P known, is then the change in the evaporation enthalpy divided by R times 1 over known minus 1 over T, the temperature where we want to know. Well, now P pressure known is we typically take at 1 atmosphere with its known boiling temperature, because they are very convenient tabulated everywhere. So these two we take at boiling, and then the rest we can follow, and then we say that the change in enthalpy of vaporization is assumed to be constant over the range we are going to investigate. So we say first that this one is constant when we go to a complete different temperature. And you have already a feeling why I'm talking about this. Maybe it's not completely true. But for sure, it shows this logarithmic behavior. And this time it is done scientifically in a solid basis. And the slope now here of the enthalpy of vaporization, the higher this number, the steeper this vapor pressure with respect to temperature, the steeper it will rise. Again, let's take the example water. We know it boils at 100 degrees at a vapor pressure of 1 atmosphere. And we also know that the enthalpy of vaporization is 40.66 kilojoule per mole. Then at 20 degrees, now we can calculate that the vapor pressure is 2,834 Pascal. Well, this is far off from the number we just saw, 2,339 Pascal. Much worse in this case than, let's say, our fitting technique. Why is that? Well, that's because, and we just said it, the enthalpy of vaporization, it depends on temperature strongly. And I will pass this one. So because of that, we are too far off. But there is another technique from thermodynamics we can use, and that is the Gibbs-free energy. So the Gibbs-free energy is defined as the A change in free energy is the change in enthalpy minus the temperature times the change in entropy. It's a thermodynamic property used to predict at constant temperature and pressure if a process is going to be running spontaneous or not. If the change in Gibbs free energy is smaller than 0, it signifies a spontaneous process. It's called endergonic. Or when it's bigger than 0, it indicates a forced process or exergonic. But finally, and that's the most important one, when it's 0, this leads to, because if this is 0, then the change in enthalpy is temperature times the change in entropy. It indicates that the system at that point is in equilibrium. It's not spontaneous, it's not forced, it is just in between. Now, when a substance is boiling at TB and room pressure PB, the liquid and vapor are at that moment in equilibrium. So that means the heat of evaporation is the boiling temperature times the entropy of evaporation. So putting this now into the Clarius-Clapeyron equation, we then get that a natural logarithm of pressure, we now do it correctly, we find it by the boiling pressure. So this is really a number and not a pressure or whatever, or a logarithm of a pressure. It is the entropy of evaporation divided by R times 1 minus the boiling temperature divided by the temperature we try to find our vapor pressure. Good. We have changed our change in enthalpy by the change in entropy. You should say big deal. Now we still don't know it. However, now we make a plot of the heat of evaporation against the boiling temperature. So what I do is I check now the enthalpy of vaporization for the elements. And I write down everywhere the number here, what you can see in this table, in kilojoule per mole. I do the same for the boiling temperature. I did it here, or some, sorry, Gamic School did it for me. And I wrote it down it is written down in degrees Celsius. Now we're going to plot these two on the horizontal and the vertical axis. Here is the boiling temperature, and here is the enthalpy of vaporization. And that's funny, because if you look here, you can see that they all follow more or less the same line. Yes, it's going up here a little bit experimental values, but many of them here are on top of this line. And this slope here now, that is of course that's the enthalpy of evaporation divided. So that's divided by the temperature, boiling temperature. That's this one, entropy of vaporization. And now this line is in fact roughly 87 joules per mole Kelvin. So it is a fixed number. So that's good news. Whereas the enthalpy of evaporation was, let's say, changing with the boiling temperature, the entropy of vaporization is not. And we can see that even though it is here not completely correct, and if I would zoom in at the very low temperatures, it's a little bit below it. Between 50 Kelvin, and if you have a boiling temperature, a substance with a boiling temperature between 50 Kelvin and 2000 Kelvin, you are pretty sure it can be very close to the 87. It's not always true. For water for instance, it is a little bit off, but that is because of the property of water is so it's a polar molecule. But most of the substances are at 87, specifically for our plasma. So now this empirical formula of 87 joules per mole Kelvin was first understood by Troughton. It's called for Troughton's rule. So it means that the entropy of vaporization is 87 joules per mole Kelvin. Taking this, now our rule of the Clarius-Clapeyron equation really makes everything very easy, because the natural logarithm of the pressure, vapor pressure we want to know divided by the boiling pressure is 10.5. We just follow the numbers, because in fact 87 joules per mole Kelvin is 10.5 times the gas constant. So we get 10.5 times 1 minus the boiling temperature divided by the the temperature, we want to know the vapor pressure. Now, okay, for instance, at 293 Kelvin, we calculate that the vapor pressure is 5,688. Wow, that's really far off from the experimental value of 2,339 Pascal. We should have used, but we should have used, let's say, the real value of for water for the entropy of vaporization, and for water it's just completely different. We would have get 2,796 if we have used this number. Still not okay, but why this is exactly happen, and the reason is that the departure of the rule of Troughton is happening for molecules which have strong intermolecular forces, like hydrogen bridges, so the polar molecules, like those ones. And it also starts to deviate when you go to very low temperatures, extremely low temperatures for like helium and hydrogen, where maybe the gas law is not truly applicable anymore. We get even quantum effects. But in general, almost all reaction products during plasma etching are symmetric arranged. That are the non-polar molecules like silicon tetrafluoride. It is a very symmetric molecule. Germanium tetrafluoride, titanium tetrachloride, niobium pentafluoride. They're all molecules where the atoms are arranged in such a way that they have a very symmetric and non-polar character. And also all these kind of compounds, products, they are typically boiling off far below 2000 Kelvin. It means that we really can apply, I think in practically all the cases, we can apply Troughton's rule without thinking. So we are allowed to say that Troughton's rule applies for everything what is going to happen in our reactor when the products are volatile. If we now put in real numbers, I take here the boiling temperature of the compound we are interested in, and here is the temperature of the reactor. And I then calculate what is the vapor pressure. Now, here at 300 degrees boiling temperature, I can see, and I would have the reactor at 320 Kelvin, so that's approximately, let's say, 50 degrees. My vapor pressure is already 25 pascals. 25 Pascal, that is, let's say, almost 175 millitorr or so. So that's quite already quite a high pressure, vapor pressure. So it means that my reaction can go relatively fast already. So because the reaction pressure, so the vapor pressure, is directly correlated to the flux. If you remember from the gas theory, that the flux and the pressure are related. But the flux of my species, which are going to be in this vapor phase, or my etching species. So it's the etch rate. So this one means already that our etch rate is sufficiently high to make sure that it works. If you go now for materials with a slightly higher boiling temperature, so in this case, let's say almost 330 degrees, you can already see it's 2.5 times slower. This will still work. And it depends now, of course, on the temperature, so of your reactor. The cooler it is, so when you would do it, let's say at room temperature, even for a gas which is, or let's say a compound which is boiling off at 300, the boiling temperature is 300 degrees, it is also going a bit slower. So it means that, in fact, if you want to etch a certain material, we have to make sure that it vaporizes. And that could mean either we have a temperature below the 300 degrees and, well, a reactor up to 50 degrees, you could see that the higher the temperature we put our wafer, or the lower the boiling temperature of our compound we have to get rid of, the better it is. So this is why we say, this is, I would say, it's still a good number, even this one. But for that reason, we say, if we now, and we know that this is true for everything because we just said it, like this is Troughton's rule. We see if we see a boiling temperature below 300 degrees, I would say that means our product is going to be volatile at the reactor pressures we are going to use, let's say at 10 millitorr, and our reactor is at 300 degrees, 20 degrees, it will work. Having this, we can put this enthalpy, so we can put it into the graph where we plot the vapor pressure here against the temperature. The vapor pressure is in Pascal, so it means here we are at, in millitorr. In torr, here we see this is the temperature of boiling here. And so it's 750 torr. Then here you see the temperature in degrees Celsius. So starting from the boiling temperature here, or the boiling point, for instance, for tungsten hexafluoride, which is around, let's say, 25 degrees at room pressure. If you then go to a lower pressure, we just follow what we did logarithmically before with water. We follow the enthalpy of vaporization. So we just follow the law together with Troughton's law into the Clapeyron equation. And it goes like this. And we can do that for any material compound we are interested in. So that can be silicon, which is way up here. It means extremely volatile. And here, tungsten is still very good. And you go down and down. Here you have, let's say, titanium tetrachloride. And it's getting more and more, let's say, difficult to vaporize because the height of this one at a certain temperature is how fast the edge can go. And here you see even a clump of materials which passing, let's say, a typical reactor condition, which is between, let's say, -20 and +60 degrees Celsius. It can be higher, of course, but these are the typical ones. And normally the pressures in the reactor in the reactive INS mode is between, let's say, 200 and 200 millitorr. Of course, here also can be changes, but this is a typical window. Now, everything which is below this window, so where this line is passing by, but it doesn't touch it, it means that the vapor pressure is so low, it will never happen. So here will be the lines who are passing here will be materials which are under that condition, not going to be etchable. For tantalum, if you would try to etch it with bromide, it means it will not work. For molybdenum, the same, it will not work. But it doesn't mean that you cannot etch tantalum, because we see here it passes the line when we have tantalum pentafluoride. And this is now the interesting part. So the top ones here are the etchable materials, and normally they are very spontaneous and therefore isotropic also. And it needs, let's say, ion inhibitor processes. Here are the mass materials, because they don't etch, or under that condition. And here is a window where it could be ion induced, where you need the ions to make sure that you can remove the material by ion impact. Now, what we do is, okay, let's check all the numbers and using Troughton's law or the Antoine parameters. If we have that available, that's even better. And with the boiling temperature and the Troughton's law, we just say in the periodic table what happens. And we say that everything below 300 degrees will get a color depending on if it etches with fluor, it's getting green. So it means everything what you see over here green is etchable when you use fluor radicals. The pink is for chemicals we are using chlorine plasmas. And here you see some gray ones, and they are etchable with carbon monoxide plasmas. The red ones, though, will never work. So the vapor pressure the boiling temperature is so high that the vapor pressure is practical zero. So whatever now if you have a compound, you will, I would say, the quick way and dirty way would be just look into this table. What is red will stay. And that means that the only way to get rid of them is sputtering by argon or whatever, with all the dimensional effects. Let's say that it will, let's say, start to contaminate your reactive ion etch tool, or will, let's say, create profiles which are, let's say, questionable with respect to would you really like that. So this, I would say, this is a message I would give for the chemistry or the thermodynamics behind the etching of plasma. So just look up here. If you want to know a little bit better the numbers, you can always try to find it and just use the theory I just gave. Good. And so we saw now that because silicon is a very important semiconductor material, it's it's the structure of semiconductor industry. Everything is caused by most of it's based on the silicon. And I try to now look a little bit more into this one because it is an ion inhibitor, a very let's say special case of, or typical case for trying to use the ion inhibitor process scheme. Now I try to go a little bit deeper into it. So we know that silicon reacts. We just saw it very easily with fluor into this volatile silicon tetrafluoride. And in a way, surface reactions, because of that, they barely have effect on the etch rate. It means that the etch rate is in fact, in a way, controlled only by the supply of fluor reticles. So it is, when they are coming to the surface, they will do that job. But it is, let's say, how many are arriving. So we have to look at it in the way that, well, we have to supply them, and it will be depending on the flow. So how many gas are we putting in our reactor? How much power? So how do we crack down this SO6, which is not etching, into the fluor radicals? Also, that one is most probably going to be having an effect. And the third one is pressure, because we know that, let's say, the Paschen curve was telling us where is the highest density of, let's say, creating the radicals. So these are three which are probably there. Now, how? And that let's do it in a very heuristic way. And we first question as, let's say, now suppose that we want to thin down, let's say, an unmasked 100 millimeter silicon wafer. And we use, let's say, for instance, 100 SCCM of SO6 flow at 10 millitorr and 1000 watts of ICP power. And I would like to know, how long does it take before I will etch 100 micrometer of this 100 millimeter wafer? How to go around that? Well, first we have to understand that STP, standing for standard temperature and pressure, that means at 0 degrees and 1 atmosphere, that for that case, 1 mole of SO6 gas is in fact gas constant, temperature divided by the pressure, is roughly 22 liters of volume. So taking that, we know then that if we have 100 SCCM standard cubic centimeter per minute, STP, SO6 is about 100 cubic centimeter of SO6 per minute STP. And then we fill in this. That means 100 divided by this 22 liters mole SO6 per minute. That means 4.46 millimole SO6 per minute. So this is what we supply. But now in a plasma. Now let's assume a very, let's say, call it a perfect plasma. And we assume that all the SO6 which comes in is broken down into SF5 and F radicals. And we assume that at the surface, silicon will react with 4 fluor radicals to create our silicon tetrafluoride. It's really not a bad assumption, you will see it directly. So that means in total, we need 4 SF6 molecules to create 1 silicon tetrafluoride. So 4 SF6 molecules will remove 1 silicon atom. We fill that in. So it means that we have 100 SCCM, SO6. It can etch then 1/4, that's this 1/4 over here, times this 4.46 millimole per SO6. So it's 1 SSM will etch 1/4 times 4.46 millimole silicon per minute. But we know that 1 mole of silicon is 20.8.1 grams. We fill it in, it means that it is 31.36 milligrams silicon per minute. We also know the density of silicon. It's 2.33 milligrams per cubic millimeter. That puts in this one, and we find with 100 SSCM SO6, we can etch 13.46 cubic millimeter silicon per minute. And the final piece is that we know it's a 100 millimeter wafer. It's a circle, so we know the area. That means that we have to divide it by the area to know how much is the etch rate in depth. It would be, if you fill in that number, it is 1.7 micrometers per minute. So 100 SSCM of SO6 can etch a full 100 millimeter silicon wafer at 1.7 micrometers per minute if our assumption is correct. So if this is true, this is, let's say, the best we can do. We cannot, in a way, we cannot go faster because we don't have more SO6 available. We just don't have it. So this is following this rule. And now we make a plot. What we do is we're going to really check experimental. We go look at the silicon etch rate in micrometers per minute. And here we change the SO6 flow inside the plasma for certain fixed values of ICP power. What you see is then that at the lower value flows, it still goes up, almost let's say linear with flow, but then after a while it starts to saturate and it becomes fixed. Why is that? Well, in the beginning, you have sufficient power at a very low flow regime. There's so much power that all the SF6 is a little bit will be cracked into fluororadicals, and it means that we call it flow limited. That the etch rate will go just linearly up with the flow. But there's a moment where you put in so much SF6 that the power of 500 watts is not sufficient to crack anymore. So a lot of SF6 is just passing by, and it will never get the let's say the reaction to create fluororadicals, and it just goes to the exhaust and it's gone. That's here it starts to saturate. Of course, if you do it at a higher, if you then increase the power to a higher value, you fix it at 1000 watts, it can go much further. At 1500 watts, even further, and 2 kilowatts. We can do the same by saying we make exactly the same plot, and what we do is we look at the silicon etch rate, but now we say, okay, let's change. We increase here the ICP power for a fixed flow of SF6. We see that more like the same curve as here. And again, in the beginning, yeah, you don't see it, but the lines, because we didn't measure it here, because at ICP of power of 0 means there's no plasma. Then again, in the beginning, it would try to follow that the more power, then you have sufficient, and then you, let's say, you have that, let's say, all the time where you have such a low flow that the power, increasing the power will have a linear influence. And again, after a while, it saturates where there's just not enough flow. So you could say, in this case, we call this range here, this slope this is flow limited, but here after when it saturates here, it is power limited. And it's just the same. If you turn around this graph, it means that this line here is for the power limited regime, where here it is the flow limited. Now, looking now at these two curves here, these two slopes, this one means a silicon etch rate divided by the flow. We call this one now alpha. It's etch rate divided by flow. And it is, if you take that one as this curve, it's around 0.04 micrometers per standard cubic centimeter. We can do the same for this curve, and we see that this one is giving us something like 0.009 micrometers per minute watt, or 9 nanometers per minute watt. And now these two we can combine, into this overall equation then. So then the etch rate of silicon as a function of flow and power is this alpha times Q times beta times the power divided by these two up. It's just a heuristic way, pragmatic way of making these two together. By doing so, we'll find, so if you have now this equation, we know alpha and beta, we know everything. So then from that moment on, we can use this two numbers to find out what will be the etch rate for let's say a certain power and flow. You can also plot it three-dimensionally, where we have here the flow going up, and here's the power. And of course, it is the same as here, but here you look in this direction, and then these curves, what you see over here, again, here you see saturation going up, and also over here you see the saturation, exactly the same what you see over here. But these two curves have more or less turned 90 degrees on top of each other, and then you get this curve. It's only to show, let's say that with this, maybe it's nicer to see that, yeah, if you want now to have your maximum performance, you probably somewhere on this line here. Because if you go here and you only would keep your power at 500 watts, it starts to saturate. So it means that somewhere here, you have a lot of flow, but you don't use it. And if you go along this line, if you say, no, I fixed the flow, then here, yeah, you use a lot of power, but useless. So you're rather somewhere where both of them are still affected by it. And that line now is the maximum of our performance. Sorry. Is it correct? Yes. Good. And now we look again at these two curves, and now look at what we see. We see now at 100 SSCM, we saw that at 500 watts, that we are hitting here, that point. It's in fact 3 micrometers per minute. But we just found theoretically that it would be 1.7 micrometers per minute. So we have double. So we are etching then much faster as our assumption. Why? And that's why we have to look at it, is that we assume here now that it was, let's say, SF6 cracked into SF5 and F. But if you go to higher powers, it's of course not impossible that you can dissociate SF6 even into SF4 plus 2F. So in fact, what happens is that at that level, where 100 SCM, if the power is very high, we are getting into a regime where we have cracked the SF6 more efficient, and we create even 2 fluor, and therefore you get 3.4. But you see that somewhere the maximum where you see where it goes down again at the highest level, that point is 1.7 micrometers per minute. And this is typically, I would say, preferable, because here we are using our power not too much in such, because here it could be that it's getting so warm and hot that although you create a lot of fluor radicals, that due to the high power, you also create a lot of temperature, and maybe you have a selectivity problem with your resistor, etc. So you rather stick maybe where you have very efficient but still relatively low powers. So it could be more advisable to go to stick at the maximum of this curve here, where you really perform, let's say, in a neat way. But as you could see already a little bit, and that has to do with the Paschen curve. It's not only the flow and the power who are, let's say, responsible for the etch rate, because we also have to check the Paschen curve, because when the pressure is very high, there will be a moment where the field cannot dissociate the ionized, the plasma anymore, and then you also don't create the radicals. And at a very low pressure, it's the same. So again, your effluence is compromised, and it will not work. That means that you can still also find an optimum for the pressure. And then we did the same by saying, okay, now we have a fixed flow and power, and we're going to change the pressure by changing the throttle valve of our turbo. So we are changing the residence time. And we find a new, even higher value. So it can be even 4 times faster. So it could be that we also come into the range where we create even from a single SF6 molecule, we create even 4 radicals. And that's, I will directly say why. But first of all, where is this maximum we just saw? So we go to this curve, and where do we find now the maximum? And yes, the maximum is for sure at the highest ICP power. So the goal, if you say rest, but then the other are fixed with respect related to the ICP power. So for a certain ICP power, if we use now 200 SSCM per kilowatt, and that is depending on this alpha and beta we found, and also the pressure is depending on it. If we say 4 Pascal per kilowatt, then it is circa 1 micro per minute at 100 SSCM. So with this one, 1.7, sorry, micrometers per minute at 100 SCM. This is what happens, how you can install your tool for silicon etching. This depends. 1.7 is again for a 100 millimeter wafer. If it would be a 200 millimeter wafer or 150 millimeter wafer, of course, this will be lower because you have your area, which we use for the calculation. When you make it bigger, of course, this will go down. But this is directly a geometrical factor. Then the optimum is SF6 plus SF5 plus F at the wafer surface. That's where this happens. But as we said, we could increase the power and then it still go up, but and we create, let's say, 2 fluoradicals out of 1 SF6 molecule. But it could be that it is getting nasty hot in a reactor. But another option is that we can increase the residence time, and that is that we change the pressure. So that's what you just did by closing the throttle valve. And we could see that the etch rate goes even further up for the same flow and power by tuning the pressure. Why is that? Is that because now the SF6, which is inside the reactor, yes, it can create fluoradicals. But if the residence time or the lifetime of your SF6 input is long enough inside the reactor, that means if we almost, let's say, for instance, if we would close the throttle valve completely and we keep it like that, and we don't have any input anymore, then the SF6 is first of all, of course, cracked into SF5 and F. But the fluor will be used for etching the silicon, and the SF5 is still there. So it will be cracked further to SF4. And also, again here, the equilibrium is shifted because the fluor is eaten up by the silicon. SF4 will be cracked. So if you have a longer residence time, you can even go down to the very low levels where all the SF6 is used up. And this maybe is would be a nice way. But of course, when you go to the higher pressure, we will see that directly, then your ion angular distribution is going to be compromised. So it could be that your profile becomes not as nicely straight anymore. But it's good to know that you can be more sustainable and using your gas much more sustainable, more better way, more efficient when you increase the pressure or increase the residence time. And now something, directly, because we were interested in this, of course, that the fluoradicals are going to be and the ions are going to do their trick with the silicon. And how do we approach that? Well, that's the black silicon method, but it is in one slide to say how it works. It's very simple. So first of all, let's say we would like to have, we need a certain etch rate. I don't know. Some people might say, I would like to have 10 micrometers per minute, and others who are much more in a nano world will say, no, I would like to have 10 nanometers per minute. But what we do, we just took the curves we just have, and we find just a spontaneous etch rates which matches with our favorable etch rates. Being it 1 micron per minute or 1 nanometer per minute, it doesn't matter. You can chase that down with SO6 flow, ISOP power, and pressure, and then you have your number. And you put in your sample, and it should be like this, isotropic, and hopefully the depth is exactly what you were aiming at, but you check. Then the next step is, what you do is you add an inhibitor. So inside your SO6 plasma, you add oxygen or another inhibitor, it can be C48, until you see that the etching has totally stopped. So in the beginning, it will be slower and slower and less undercut, and there's a moment where everything stops. Let's say below 5%. So what would you see like this? And now we say, now we switched on the CCP power. So here we did the etching with, let's say, the ICP power. So that one is generating the radicals, but no DC bias, as we remember from the previous lecture. And now we add the CCP power, so that's the platen power, to create, to extract the ions from the plasma generated by the coil power. And they will knock away the inhibitor, and you will see then after sufficient power, in the beginning maybe it's hesitating, but then you have sufficient power, you will see that you come back to the original etch rate at the bottom, and that's where we hit our maximum performance. As easy as it is. But now we talked about it. What's the etch rate at 100 SCM? Let's say for the best and nicest performance is roughly, for a full 100 millimeter wafer, it was 1.7 micrometers per minute. Now we put in a wafer, but the wafer is not 100 millimeter bare silicon like we calculated before. That means that the silicon loading is less due to the pattern. What we should do now? Well, we know that we calculated here for the 100 millimeter, that is this area. But if we have now a silicon loading of, let's say, 50%, then our area is, instead of the 100 millimeter wafer, it is 50 millimeter or something like that, or half of it. Sorry, it's not 50 millimeter diameter then, but it's then half of it. That means, of course, that the etch rate will be doubled, because we are going to etch the same amount of material. Well, this is, I think it's a formula of MOGAP, who first came with this. This is conveniently expressed as the initial etch rate now is, let's say, called a saturation etch rate divided by 1 plus a constant times the loading. Well, look first when the loading is very high, then you see that then the one can be taken out of it. So then is the saturation divided by CL. So at sufficient high loading, the etch drop will drop 2 times when the loading is doubles. So that's what we more or less used here. 100 millimeter, 1.7. If it would be 50% loading, so then it would be 3.4. But if you go further and further and you make your sample smaller and smaller, there's a moment where our initial thought that the etching will be totally independent at the surface, so that everything happens very quickly, it is just not true anymore. So you get diffusion problems, you get temperature problems at the surface, and it just cannot go faster. So the supply, so the final reaction is not fast enough. This one here, this number here now can be controlled by temperature, and this one is more or less controlled by amount. And this is how this curve works. Then a second thing I would like to add a little bit, because it comes back also in the second part of this, is that the etch rate depends on the aspect ratio of features. That means here you have a cross section where you see after a certain time of etching that structures are etching deeper into the silicon. And this could be, let's say, 10 micrometers, 8 or whatever, going down, that you see that a few very things. Okay, it is a few things we can observe here. Well, it's nicely down, but you can see that the structures which are smaller are not that deep as the big ones. The reason behind this is, let's say, controversial, but let's follow the Knudsen transport limitation. So what happens is, why is this one faster, or in fact, why is this one slowing down? Well, radicals who are coming in or you would like them at the side walls. We said already it is protected and therefore it will not etch. And the bottom is all the time hit by ions and the radicals will etch away. But it means that here at the surface, it will be saturated with radicals or fluor radicals, but they cannot etch, and they are there, but at a certain moment, maybe they are rejected again. So they come in, they stick there for a little moment, and after that, they will be ejected again. But it doesn't remember that it came from this direction, and it can go in any direction randomly. That means there's also a chance that a radical which comes in, it will go back. It can go there, there's a chance over here. And then, but when it goes inside the trans deeper, that's also, let's say here, in this case, it would be maybe 50% chance. Again, it will hit this one. And again, the same problem. It will stick here for a while and can go up and down. Again, maybe 50% chance it will go down, but 50% going up. And you can see that all the time it will knock at the wall. There's always a reasonable chance that it will go back. That means that the more times it will hit, the more it will go, let's say the bigger the chance it will be just going back. And that's a Knudsen transport. So it means that high aspect ratio structures here at the bottom, much less radicals relatively will reach the bottom than for the big ones. And that's REA lag. And it will follow roughly this formula. It depends, but roughly. So that's the basic idea. Smaller structures at slower. And now we're going to talk, let's say, before we coming close to a break, about the directionality. And that means including the ion distribution function. No, well, the energy and angular distribution of ions striking a substrate surface, they are, let's say, really among the most important parameters in directional plasma etching. The ion energy distribution, or IED, of impinging ions determines now the surface reaction rate and therefore affects etch rate and mass selectivity. The ion angular distribution, the IAD, determines now the spatial variation of the ion flux along the walls of etching feature. If ions have a very narrow distribution, like here, then most of the ions strike the feature at the bottom. And in contrast, if the ions have a broad distribution, like here, you will see that ions also will hit, maybe with sufficient energy, the sidewall and knock away the passivation layer over there. That results in undercutting, bowing, bottling, and a loss of anisotropy. Now, a convenient way to describe the possible anisotropy, that's what we call the anisotropic number. And we will talk about it now. So what happens, in fact, we have in the plasma, we know we have a lot of ions and we want to extract them towards the wafer. And that the energy with which that is used is the plasma potential plus the DC bias. Now imagine that you have this ion here inside the plasma with this ion temperature, KTI. But inside the plasma, we know there is no electrical field. There is no reason why it would go with more chance downwards than upwards. So it's isotropic. It moves in a random direction. But there are always a few of them who are passing by the boundary between the plasma glow and going into the dark space where the electric fields exist between the plasma and our wafer, which is located over here. Then, due to the electrical field, the ions are going to be getting a certain directionality. They are accelerated in, let's say, this direction, downwards to the wafer, the normal direction. Of course, the ions have still the energy sideways, their let's say, original thermal energy. But the ones who are moving towards the wafer are accelerated by, let's say, if you are at a quarter of the dark space, it's a quarter times the charge of the ion times the potential difference between these two. When it's halfway, of course, it's halfway this energy coming in. So the ions are moving faster and faster with respect to the rest in this forward direction. Sideways, it's still the same as KTI, but the directional point is getting stronger and stronger. Here, when they now reach the surface, it has its maximum. So then it's still this isotropic one, the thermal one, but here is our energy which has been gained by passing the dark space. So our ion angular distribution has been sharpened. Here it is very broad, and it's getting sharper and sharper and sharper, where here is at the maximum. Now we can define this directional part, here, with respect to this isotropic random temperature of the original ion temperature in the plasma. That's beta. Beta is then the elemental charge of the ion times the plasma potential plus the DC bias, that's the bias gained in this dark space, divided by this isotropic one. So with this, it can be now shown, when you have this one, that the ion angular distribution function is given by a Gaussian distribution. So this peak here, when you look at all the angles here, it is Gaussian. It's a constant times an exponential function minus beta squared, which is roughly the cosine function times 2 times beta of the theta. Typically, beta is much smaller than 1, and then we would get that the full width half maximum, so that's somewhere here, is roughly 100 times divided by the square root of beta. Now let's take a typical example where the ion temperature inside the plasma, it's a cold plasma, so it's quite close to the gas pressure temperature, so our room temperature a little bit higher, maybe 400 Kelvin or so, or let's say 100 degrees. And we supply the plasma, let's say latent power that it creates, let's say between 10 and 100 volts. We can fill in that number in this equation, and then we find that the beta is somewhere between 100 and 1000. It means that our Q is half maximum is between 10 and 3 degrees. So that's the sharpness of our ion angular distribution which is coming in. What is important here now is that we know now how we can calculate that one. And then the final piece here now is, before we give a complete consequence of this, is that we already showed in a previous session, the previous lecture, that if you go down in pressure, that the electron temperature is rising. And with it, let's say, we know that the plasma to floating potential is also rising. It's roughly 6 times KTE for SF6. If you remember that one. And that's important. So now we have here that this is the number we just saw in our anisotropic number. So the pressure, the lower the pressure, the higher the energy gained by the ions in the dark space. So now we can say that if we now want to make a structure where I would like to have the ion striking the surface as straight as possible, we don't want an ion angular distribution, let's say with an full width by half maximum of, let's say, 40 degrees. It would be really starting to bow or to bottle my structures. It would not be straight. I would like to have a few degrees or so. We can calculate it now, because what we can do, if we just etch it and we say, oh, it's not good enough, we can sharpen it. We know now by lowering the pressure, because if we lower the pressure, then the plasma potential goes up. We know that one. Another way of increasing the beta is getting the DC bias higher. So we just have to increase the self bias. So that means probably the latent power should be a little bit higher. And another technique would be to get the ion temperature down. What would it mean? Well, some reactors are heated up the walls, let's say up to a few hundred degrees, or maybe 150 degrees. And that also will not help. So we would rather have them cool down the chamber walls, or keep it at room temperature. That's also improving, because then the isotropic behavior is less. So there are then the techniques to make it as sharp as possible. And there will be a moment, of course, you cannot go further because there's you have to take into account, let's say, I think I did it not here now. But let's say that at lower pressure, because of the high bias, you have to also take into account that yes, the directionality is better, but also your mask is under higher bombardment. So it could be that your selectivity is going down. So you have to be willing to live with compromises. Well, I just skipped this one because of time, but you can see a little bit still later on if you want to check. That means that now it's time for a break, 5 minutes. And after that, we will use all the pieces we have taken into account now to go for really the experimental results from the know-how we have gained here. So hope to see you back in 5 minutes. All right. All right. So now we go and continue with the experimental section. What I will do is give an overview of, let's say, a little bit of history, the mixed halocarbon and mixed oxygen processes, and then switch quickly to the switch processes, Bosch, DRAM, DREAM, or switched oxygen. And then I will talk a little bit about selectivity, ultra-high aspect ratio structures, and switched chromium etching. And then finally, three-dimensional sculpturing. Due to time, maybe I will skip the switched chromium etching. I will see. First, what is mixed versus switch mode in what we say in the ion inhibitor reactive ion etching? Well, in mixed mode, what we do is all the stuff has been put together in the simultaneous in the same time. That's the normal reactive ion etch mode. You have a gas like SO6, and then we were etching and we put in oxygen until it stops. We do that at the same time. But the other technique is that you do it in what they call the switch mode or the pulse mode, where you etch for a while, and then you deposit, let's say, a passivation, and after that, again, you etch for a while. Deposit for a while and etch for. That's a switch mode in time. Well, start with the halocarbons. So the early years, and we are talking about 40 years ago or so. There it's more for me what I call it now, maybe plasma figures. We select a little bit negative saying, but a little bit randomly an inhibitor and publish and hope for the best. So you can see that the profiles are not perfect, but it's for sure much better than the moment at that moment, where wet chemistry was the normal one. This is, of course, much better than the isotropic results from wet etching. But in general, if you compare to state of the art, it is poor selectivity. The reason is that the bias in this mixed process is all the time there. You can see that the selectivity between maybe photoresist and the silicon is maybe up to 2 or so. So silicon can only go 2 times faster, or the oxide is going 2 times faster than the resist as a mask. And they could improve that by processes where there's less deposition of inhibitors, so you're a little bit more to the point. And then the mixed, let's say, oxygen process, so that's SF6 mixed with oxygen, became quite popular. And it showed really already a reasonable selectivity, as that can go up to 20 or so easily. However, you can see already there is some problems here at the top. And also, if you now look, it comes with a weak sidewall protection, and the profiles become pattern dependent. So this one is positive tapered in a way, this one is maybe straight, and this one comes already with negative tapered. So it works now in a mixed process. The reason is that it works with compromises. You might want to have a high etch rate, and then you're asking for a high ICP power and flow, thus giving a high reactor pressure. But you also want a straight profile. So there's just a narrow ion angle distribution function. And that means a low pressure, as we just saw before with beta, with the anisotropic number. And you also would like to have a high mass selectivity, and that is asking for a low plating power. But again, as we saw for the anisotropic number, we need a high plating power to get this ion angle distribution very strong and very sharp. So this is the consequence that both processes are running in parallel, both the etching and the passivation. Now we can remove that dilemma by putting it into a cycle, the switch process. I will start with the typical one everyone probably knows in the audience is a two steps Bosch process. It uses now then a sequential inlet of inhibitor, which is passivating a process, let's say with C4F8. And then after that, for a little moment, you go to use an S-gas. There's at that moment you supply the DC bias, and of course in the beginning it still has to remove the fluorocarbon we just deposited here at the bottom, but when it's gone, it will continue with etching. So although it creates, by doing this in the cycle, it creates scallops, what do we call these things over here? So 1, 2, if you go every step, you get these, this will continue. It's called scallops, but it's also going to be nicely directional. For instance, if you would check with the mixed mode and you compare that to this switch mode, you can see that, well, the passivation at the top, so that one is gone. It's much less pronounced, and also the profile dependency, it's much better in this one. And also because we are not using all the time the bias, but only in part of it, the selectivity can be much higher than the mixed mode. But we can do it even better. And as well, we can even split it, because just beforehand I said, let's say when you have after depositing here the fluorocarbon, initially the etch process will not do anything because it still has to remove the bottom. So we can do that in a separate step. So we say we deposit the layer, and now we are having a step which is solely removing it at the bottom, but then we can take it away because after that we're going to etch, and that's again a spontaneous process with only radicals, and the silicon will etch isotropically, creating undercuts. That means that we have created an even higher selectivity. So, and that's another part which is now becoming important, because the mixed dilemma between high etch rate or perfect dead actually is removed by this 3 steps process, because now we can put here a high pressure at the deposition, and there's no bias, so that means the mask is preserved. And also when we etch, the final step, we can do all that also without a bias. So we need only the high bias very locally to remove at the bottom this deposition we just took over here. And that then can now be done, let's say, at a very low pressure. And here we have a very sharp ion angle distribution. Furthermore, now we can choose the correct balance. So we can really take this step here and tune it in such a way that it is just gone. So we have to, we had deposit here a layer, and that means that we tune this time here such that this is just gone, and then we etch. So we can really have an extreme high selectivity. And because we deposit everywhere, let's say maybe uniformly the same layer, it can be even infinity. So if we really put it correctly, we can go to extreme high selectivities. It can be even that because of the structures when they get higher and higher, like before, we saw that RDA lag is going to deposit less at, let's say, high aspect ratios. It's not only etching less, but also the fluorocarbon deposition will be less at the bottom of structures. That means that at the top there's a little bit more, and then when you etch with the ions, the bottom will be freed earlier, whereas there's still something on top. So it could be even that instead of silication or infinity, that your bottom is still etching here, whereas on top it is even growing. That are, of course, very unique situations. Normally, you're already happy that you have a very high selectivity caused by this. But there's another thing which is really nice that we can use, is that we can increase the etch time. So while we have done this perfectly matching deposition and remove step, the etch step is free to be whatever. And we can use now what we call ramping. So during every cycle, what we do is this time can be slowly increased. And we saw before that REA lag is causing that while you go down, due to this Knudsen transport limitation, it's getting slower and slower. So less and less radicals are etching here. So although the time has been here the same for the whole cycle, when you go to the high aspect ratio structures, it cannot etch that deep. Not all the radicals are reaching the bottom. But now, if we see that this, and this is the side wall of this structure. So when you look, this is the cross-section view. If you break it along this line and you look at this direction, you will see these lines are here. So this is also a view of the sidewall. And now we can compensate for that. And we can say, okay, in the beginning, our etch time is maybe short, but we make it longer and longer to compensate for this Knudsen transport limitation. And that's what happened over here. So we have then the conventional process where we don't do anything with ramping. And now we're going to ramp it. So all the time when we go down, we're going faster and faster. So now you see that the lines are at the same distance all the time. We just compensate for that. So that's the E-time ramping. Doing this, we can go now already to very nice high aspect ratios of 50. These are pillars. And I would say, yeah, the top and the bottom, they look, yeah, you see, of course, the classic scallops, but for the rest, they look pretty much okay. But yes, the scallops are, let's say, what we call part of the deal. But there's something else is going to happen, and that is there's fluorocarbon deposition all the time. So every step we do a fluorocarbon deposition, and I said before already, at the top side, it can tend to be depositing more. Let's say that at the bottom. So at the bottom, we would like to have still a good enough passivation, but that means we more or less overreact at the top. And you can see that here that the fluorocarbon is slowly coming together. And when they have a very small structure, like here, what you can see here, they can even start that they close the trench. So, of course, you can try to do that by proper tuning and saying, okay, I'm going to do a little bit less in the end, etc. But there's a lot of compromises then. But what you can also do is when you see that, yes, we know that the thickness at the top side, it's starting to grow a thicker and thicker layer, which starts to close the trench. So you could say also that at the bottom, and that's what you will see. The best thing now to do is let's go and try to see after having do the final etch. What we do, we etch away all the fluorocarbon. So we take an extra step. It's called the dream process. So before that, if we would not do this at all, then because it is closing at the top, the trenches are getting smaller, and therefore also at the bottom it's getting smaller. So you get a very nasty positive taper, and it might be even stopping at the moment where it closes. But now if you then increase the oxidation, so after you have done, let's say, in every cycle we knock in an extra oxidation step to etch it away, then you can remove that one, and therefore it stays open, and you can see that after doing this, if you have the dream process, it just stays nicely straight. Now, okay, we did it with fluorocarbon, and we saw the pros and also maybe some cons. And now let's say we go back to the original one. There was the mix process with oxygen. It showed let's say a low mask selectivity, because everything is all the time at the same devices all the time supplied, with some undercut at the top. And as for really time-consuming process development, also because the profile are changing from positive into negative. But when you're using, let's say, solely oxygen as the inhibitor, there's not that much process drift, and it is very tool friendly. So the tool is so the plasma reactor is very easy to maintain. There's no dirt coming into it. Oxidation is a self-stopping process. It's fine. Then you have the fluorocarbon inhibitor, like we just with the CIS process. It causes process drift and reactor contamination because of this. Fluorocarbon is not only going to be deposited on my sidewalls of my profile, but also in the reactor. And you need a lot of cleaning and conditioning processes. And they are also a little bit, let's say, unfriendly for the environment. And scrubbers are needed to remove them. But they are, let's say, operator friendly, not tool friendly, but operator friendly. And it creates a lot of design of freedom in 3D options. Now, so this one is, let's say, good for the machine, and this is good for us. How can we combine this? Let's go back to how we add silicon in the mixed mode or in the switch modes, and we have the fluorocarbon inhibitor with C4F8, and we have the oxygen inhibitor. We know these. This is conventional. That was, let's say, the original ones done, let's say, 40 years ago, and then these came in later, also cryogenically normal. And then this is the Bosch process. But you see another switch process, which is S6 oxygen, which has not been used, let's say, until recently. And that's the core. So what we do in the core is, it is like the Bosch process or like the DRAM process. But now we say, instead of fluorocarbon, we use oxygen plasma to oxidize the surface. And then again, we can do remove step, and we etch, and we going back, and the clear step. The clear step is there because what we have here is products, silicon tetrafluoride. But if you do directly the oxidation, it might be that they are already oxidized inside the plasma reactor while they are still close to the wafer, and they might create silicon oxide particles, and that creates black silicon, what we call, and I will come to back that later. It's not always needed, but the steps are exactly the same as the Bosch process. And you can see that if you do so, it's totally fine. So you have structures which are just like the Bosch process. They are straight, a little bit positive tapered here, and nothing different. But the only exception is that this one is tool friendly. So that means very reproducible and reliable. The S-rays, though, are much lower. So typically you will not reach, let's say, 20 microns per minute, but that's a different subject. We are anyway going to be more and more inside nanotechnology. Therefore, also we are looking at nano edge rates. So in a way of saying, so it's fine. And it can go down to the very small scale because now we don't have any fluorocarbon deposition, so no clogging or whatsoever. It's oxidation. It is, and I will directly talk about this one. Why it is so nice. You can go down to the very small scale, like here, 30 nanometers, and you can still see the scallops, but they look cool and they look down to the smallest level, very okay. It has also no, in this case, what we call notching. I will not go into detail, but that's also something which is not pronounced for the core process. And now I tipped it a little bit, and that's black silicon. That is the roughness which is sometimes created on wafers, and which can be, some people like it and are annoyed by it. Now, first, what is the root cause of black silicon, and can we create it? As we know, so black silicon for solar cells is where we really do use it in a positive way. But for microfluidics, where we would like to make flow channels, we want it to have to be as smooth as possible. So we have to find out where it's coming from. And now let's first look at a silicon wafer. We have here a zoom in, and this is a plain wafer of silicon, and we put it into, we did our best to clean everything. And we put on, let's say our core process or a Bosch process. And what we do is doing the bottom removal step, we didn't check it very carefully. And it seems to be that we did not remove maybe everything correctly. So during the bottom removal step, so that's the step where we had the high ion flux, we are trying to remove the oxide or the fluorocarbon, but there's something left. And that will then create, let's say, little particles which are leftovers, and they are what we call then a micrograss. And they will end up in every cycle, and when there's not enough under edge, they will really create pillars, and in the end, it will create black silicon. Looking at the whole scheme, there were all kind of possibilities where it's coming from the reactors, from maybe dirty wafers, but two of them are always there, and that is where, so you can get rid of all the others, but if you don't, in the switch process, if you don't remove your oxide or fluorocarbon at the bottom of your structures during the removal step correctly, you will create black silicon. And then we look further. We see that there are two distinct differences between the Bosch process and the core. So for the Bosch process, we see sometimes in big open fields, we see a lot of grass, whereas the smaller structures are nice. But for the core process, it's either everything is clean or everything is black silicon. So in the big open structures, but also in the smaller ones. Why is that? Well, let's go first for the fluorocarbon process. So what we did, it was that we deposit a layer, then we remove it at the bottom with the sharp ion distribution, and then we etch it again with the fluorochemistry. But because of the deposition is coming out of the plasma zone, like the etching, where we had REA lag, where it's going down in structures, so the smaller structures are etching slower. Also, the deposition is doing the same. So the big open structure, like low aspect ratio structures, will get a more fluorocarbon on the bottom, let's say, than the smaller ones due to let's say the Knudsen limitation. That means if we then go to the the removal step, then because there's much less, and the ions they have no removal lag at all because they're all going straight. They don't bother about the wall at all. It means that at the smaller structures, they tend to be already free from this fluorocarbon in the earlier states than the big ones. If you then stop a little bit too early, then this one can be already clean, but this one is still there. There's still some fluorocarbon. If you then continue, that will be our, let's say, nanograss, micrograss, whatever you call it, and creates these pillars or black silicon. That means at the big open structures, you will start to develop grass, whereas in the smaller ones, it's not. Now, core has something else because core is using oxidation, but plasma oxidation is self-limiting. So it means that if I take an oxygen plasma during, I try to make the inhibitor and I want to oxidize the silicon, it just stops after, let's say, maybe a few nanometers. Here you can see the time. It takes almost more than 1 hour to grow 3 nanometers of oxide. So it's a very thin layer. And already after, let's say, a few seconds, it's already 1 nanometer. So it's a very quick logarithmic process where only in the beginning it is there, but then after that, it doesn't do that much anymore. That's what we call self-limiting. So what are the consequences? Then if you now look at the plasma oxidation, there is no deposition or removal lag because so there's no deposition lag because the oxidation process, when this one is of course much faster, let's say after half a second it's already there, but after 1 second it doesn't go further that much anymore, whereas this one is still gaining. So after maybe 2 seconds they're already identical, and then after that you can continue, but there's no much big difference. And then you continue again with the bottom removal step, but now because they are having the same thickness, they are removed in the same way. So either you have cleaned both of them and you can create a very nice directional profile without any roughness, or if something is left, it will be here, but then it would be also here because they had the same thickness and the ions don't see the difference in the structure height, in the aspect ratio. So either everywhere grass or not. So that's why you have it. And in that way, you can tune it now very nicely. So or you put it into a mode where everything is nicely clean, or you didn't do it sufficiently and then there's grass. You can also say, okay, in the beginning, I etch very nicely. And then suddenly after a while, I say, and now I switch my plasma to create at the bottom, let's say black silicon. What you can also do is that meanwhile, after doing a certain etch, I clean the top, the resist, it's removing it, and then also the resist, also the silicon on the top will create black silicon. So you can more or less now play with your tool to say, I would like to have roughness on the top, or I would like to have roughness everywhere. You can say wherever you want. And then, okay, now we have to talk a little bit more about etch selectivity and mass retraction, because that's becoming a very important subject. You cannot always use photoresist because the selectivity, especially with the core process, which is using oxygen to etch the silicon, cannot be that much higher, let's say, than roughly 10 or so. How can we improve that? Let's first look a little bit what happens with resist. Imagine now we have resist this on top of a silicon wafer and we start to etch. In the beginning, we will go maybe nicely down, but because of the oxygen in our silicon etch process in the core, also the resist will what we call retract. It's not only etching from the top side, but also sideways, because it's the radicals are etching it away from all directions. It's isotropic. But that means that after a while, the retraction is so much that the top side, which was originally there, is also going to be under attack. So that means that after sufficient etching, deeper and deeper, the sidewalls are going to be under attack, where the resist is slowly retracting. You can prevent that by, for instance, putting there a silicon oxide on top, and that is protecting the top side, and then it will stay nicely clean. So this is the same process running, but here there was a protective layer. But even silicon oxide has its, maybe the selectivity is 20. It doesn't retract like photoresist, but it's getting still thinner, and after a while it would be also a no-go. So therefore, we would like to look at other hard masks, and for instance, that's chromium, which can be much higher selectivity. What we first do is we pattern it. In this case, we do it with lift-off technique. But the end result is that we have a chromium pattern on top of a wafer, and then we're going to etch. It's either with a deep UV or with the E-beam. It doesn't matter that much. Doing so, we can reach now, because chromium has an extremely high selectivity. And that one, chromium is not directly, when you oxidize chromium, is not directly being under attack. Not completely true, but much less. And in that sense, you can have a very thin layer of chromium where we can create structures with aspect ratio. Let's say here you see 55 for 200 nanometer pillars, or here for 60 nanometer pillars. And because we are using chromium as a mask, we can use the oxidation much longer. So instead of, let's say, for resist, we could not go that far because the retraction is so strong that our selectivity would be compromised. But for chromium, we can go to a much longer one to make sure that everything, when we have high aspect ratio structures, that everything, even down to the very bottom, is strongly oxidized enough to get the self-limitation working perfectly. Doing so, we could see that if you etch deeper, that is getting higher and higher. The structures are getting nicer, but we located also that, hey, but the chromium is still etched. You can see a kind of a retraction even for the chromium. It's much, much, much less than resist. But if you go for the extreme high aspect ratios of 50 and more, it becomes prominent. So that's why we could find out that in fact the chromium is etched by fluorochemistry when you combine it with the oxygen. And that is because for chromium etching with chlor, we know that the product is chromyl chloride, well known, and these chemistries are used to etch chromium. Where they mix oxygen with chlor, let's say 50-50%. But you can do the same with fluor. And that also, fluorine will not directly etch chromium, but it will attack chromium oxide. So in a core process where we oxidize it all the time again, in every cycle, we are more or less creating every time a layer of chromium oxide. That's the reason why it is etching. I will not go here due to time, but you can later on look it up for yourself. But what happens now for chromium etching is that, yes, if we start now with pristine chromium, the first what could happen is you oxidize it in the core process and you create chromium oxide. But the chromium oxide can be directly etched by fluor. Not the chromium, but the chromium oxide can be etched, and it's removing it. But then after a while, it will be fluorinated. But this one can be knocked away very easily, the fluor radicals, by ion bombardment. And then again, you can back to the chromium layer, which then can start again to be oxidized, and you go in a cycle. You can call it a type of atomic layer etching. Good. So then it is in a switch process. Here you see the process flow parameters. It's quite a very small number of fluor to make it work. So it's quite 3 SCM. That's a very low number if you compare, and only 1 second in the total where the oxygen is 50. So it's like 1% in total, something like that. But looking at that, now we can have this one chromium as in a complete mode, where we have the core process running not only for etching the chromium hard mass, but also the silicon. That means we can go, let's say, for bulk silicon, we have, let's say, a layer of chromium we put on top of polysilicon. This one is needed to etch the chromium. I will see it directly. And there's now, for the DPV, there's what we call a bark layer. But it is not really essential for this story, and a resist on top for the DPV resist. So what the first thing you have to do, and that can be done all in a single, in a multi-steps single run for your reactor, is first you etch with a very low pressure of oxygen, you etch the bark layer, so that you are opening up the polysilicon. Then again, with a very low pressure, you use, let's say, a continuous mode of SO6 plus oxygen to etch away the polysilicon. Then you can strip the photoresist. We don't want it to have anymore. And then we used the polysilicon as a mask to etch inside the chromium. And after we have done that, we can etch with the core process inside the silicon which is beneath it. So we have now, after we have created, let's say, a wafer with our hard mask set, it can be evaporated chromium silicon. So it's relatively easy to do. Then you go to your lithography, and after that, you can do all the steps in the same process, all done with the core process, where the reactor is very happy and reproducible, because it will not cause process drift or let's say contamination of the reactor. For instance, if you now look at it, so we have here 30 nanometer chromium dots on top of silicon, and we etch for a certain number of cycles. You can see here how much that could be, like 100 or so. And after a certain moment, it is 1.5 micrometer, 4 millimeters deep with an aspect ratio of 7. And we just can go deeper, 8 micrometers deep, aspect ratio 40. You see how nicely straight they are. Here we turn it 90 degrees, and so you can see here the line, how nicely it follows the extremely sharp ion angle distribution function. So we really go to the low pressure during the bottom removal step to make sure that the ions are only removing at the bottom, and that they don't hit at all anything from the sidewall. And that's saying we need a very sharp one. We could do that because it's a very short time that we need it, so the selectivity can be still very high. But if you go beyond aspect ratio 40, we can already see some problems with, while we're looking into the SEM, that the structures are so slender, so these pillars, that while you are looking with the SEM, they start to vibrate. So the charge in the electron, while the beam is scanning, is charging one of them, but then it's attracted to the other one, or it's repelled for the other one, and therefore it touches the other one. And it's possible even that they start to touch and they merge. They just, let's say, they click together and they don't want to remove anymore. This is why you see this kind of vibrations. It's not because the structure itself would vibrate, but it's because of the electron charge. The electrons are charging it, and they start to move around with respect to each other. It can be that far that they really start to cluster. So here we looked with the SEM for a while, and they all click together. You can see that the rest is still fine. So it is caused by the how we look at the structures. The closer you look, the stronger this effect is. If you would zoom out, it will not happen. So it's about how much electrons you bombard on it. So if you then don't zoom in, then you can see they are nicely straight, and then again go up to extreme high aspect ratios, maybe up to 130, what you can see here. Very slender structures, and maybe it's funny to see. So you can go to very high aspect ratios and no that much compromises, and a hard mask is sufficient to survive that long time. You see, even when you look at the cross section, nice optical phenomena. Will not go in due to time. I will not go into detail here because I would like to have at least a last quick shot on the 3D sculpturing, because while we are etching down and we are now in the switch mode, we are allowed to program after, let's say, a certain amount of scallops, maybe 10 small ones. We can say, now we stop. I will make a little bit thicker passivation, and I'm going to undercut much more than previously. So it means that all the time I have the same number of etch time doing my, let's say, Bosch process, but in one step, I do it a little bit longer. And after that, I again continue with the original one, and again, a long one. A long one. And that's what happens here. So what we do, we add many little scallops and then a big one. Many scallops and a big one. And what you can see over here. So you can call it, let's say, a nano sausage, but the more scientific name would be a modulated pillar array. And you can see that here, what we did is here our original mask. Let's say 10 small ones, a big one, 10 small ones and a big one. Well, doing this is then already really 3D engineering. We can make even structures where the pillars, if I would go too far here, the pillars would just drop down. But if I have the inverse, so a membrane with holes, then I really can undercut it, and you get this, what you say, many layers of membranes on top of each other. And even the distance between these different levels here, I can tune, because I can program it. And we did it with this one, where we could create even a photonic gap, band gap material. But the important to know is here, this one has been done directly in a single run. So it's just a recipe. Yeah, you have your mask on top, and the machine is doing, you drink coffee in the meanwhile, and this is afterwards created. And then you can create many other things. Here you have see benches. I don't know what to do with it, but it is funny to see, and maybe for other people it opens their eyes. Let's say, hey, but if you can do this, can we also you can create maybe for people some new ideas. But let's say this was all done with fluorocarbon, so that was originally when we let's say did some progress in let's say Bosch processing, but we knew that the Bosch process is having step coverage problems below, let's say, these scallops. If we try to do this 3D engineering, the bigger ones, sometimes you see here a gap, and that what happens after a while, if we want to undercut a long one, that they are eaten up here, that this one is maybe not protected enough, and that the structures are eroded away over there because of the radicals. That's because of this, let's say, deposition lag of fluorocarbon from the DRAM process or the Bosch process. The core process, though, doesn't have that problem because it doesn't deposit, it oxidizes, and you just do it long enough to make sure that everything is oxidizing. And then the structures are much better preserved, and you can go to many really wild structures. Here we just tune it. We make a recipe where we say a big one and then we learn a little longer. So we just create something totally random here, but we have programmed it to make sure that we can show that we can do the undercut, the length of the under, how long we do it. We do it on our own will. So we say controlling it. But also, like before, by playing now with how fast you do it, you can make positive tapered or straight, and let's say even maybe negative, and you can force that even further. And then you can say you can make them straight here, like you see, but more positive, very positive. So you can more or less by tuning now the steps times. It's typically only the times we are tuning. We can play and tune the profile as we like to. And that can be even, let's say in the beginning it's positive tapered, and that we say after a while, no, and now I would like to continue with a straight one. And that is what happens here. So we can try now to say, okay, I would like to in the beginning straight, and it's a little bit negative. Here in the beginning, I had big scallops, and then suddenly I say, okay, and I stop, and I make now very small ones. I can also say I make it very positive, and then I start with creating black silicon at the bottom. So we are getting more and more, let's say, ability to say we want a certain structure, and we program the tool. We just say how long it should be in that step, then it goes to the other cycle where you have a different ratio between the different time settings, and you can then create, let's say I would say quite astonishing, nice features. And that mean that I try to see, can I go to Saturn, so the rocket, to make a copy of it, and let's say we try to copy it and looking at what are the numbers when you look at this rocket. And in that sense, yeah, I was able to make it down to the nanoscale. And that's I would say just by saying into the recipe for, let's say, etching this machine. So this is the plasma recipe, writing down. You can make, after you have done your chromium mask, you can say, first you make your top cone, then you make it straight, another cone, straight cone, that is here, straight cone, straight cone. And the time, how long you take, will make how the final structure would look like. That brings it to the end. And sorry that I overreact a little bit with the time, but that is what sometimes happens. I guess it's now time maybe for some questions.
Yes. Thanks again, Henry. That was amazing. I'm very impressed by what is possible with modern tools, nanosausages.
Yeah.
Amazing.